Easy BTech, your guide for BTech and beyond. In the today's lecture, we will discuss about transistor as a switch. How the transistor can act as a switch and what are the switching operations and how the transistor can act as an amplifier. That all we will discuss in the today's class. Okay, students? Transistor as a switch. Transistor as a switch. Now you can say there is a transistor, NPN transistor. This is collector terminal, it is base terminal and it is emitter terminal. And this emitter is grounded and this resistor will call as an RB. Now we can apply input across here. This will call as a V in. This is VCC. We will take output across here. This we will call as a VCE. Voltage across collector to emitter. It is a one loop. The current in this is the base current IB. Okay. This is the circuit. This transistor is a BC107. BC107 is a model. Now you can see, and the type of transistor is NPN transistor. Okay, students. Now you can see when Vi is 0, when Vin is 0, when Vin input voltage is 0, what happens in this particular case? It is like the transistor, you can see here, it is an emitter terminal, it is a base terminal, it is a collector terminal. Now it is operated in forward bias, positive connected to positive of the base. Now it is a forward bias. Okay, but when you are giving Vin is 0, then automatically a base emitter junction will operated in a reverse bias, due to which the transistor can act as an open circuit. Okay, when Vin is equal to 0, the transistor act as off switch across the JE junction, that is emitter base. Okay, now this is emitter is N and base is P. It will act as a off switch. Then the response will be like this, that is this is RC and this terminal is open circuit and we are taking an output across here. This is V0. Now from this you can see here it is VCC. Now you can see from here Vout is equal to VCC. It means due to this open circuit, suppose you can connect a LED or anything, you can connect here LED. Construct an LED. LED will be close. This LED will be on state. Okay, because this VCC will drive like this. Is it clear? Okay. Similarly, when V in is 0, the transistor can act as a off switch. Similarly, when V in less than VBE, when V in less than VBE, in this also the same, the transistor remains off state. The transistor remains off state, that is IB is 0 and IC is also 0. No current flows in the transistor. No current flows in the transistor. Is it clear? This is the switch operation. Next case you can say here, when V in greater than VBE, where VBE is cut-in voltage of the transistor, that is, if it is a silicon, it should be greater than 0.56 volts. If it is germanium, it should be greater than 0.2 volts. Or similarly, we'll approximate this. Current can conduct after 0.6, and the current through the diode below 0.6 voltage is a negligible current. Below 0.6 voltage, the current through the diode is negligible. Above 0.6, the current through is a rapid increase. It is also the same man. When V in greater than VBE, similarly in this case what happens? When V in greater than VBE, the transistor remains in off state. The transistor remains in on state because this emitter base junction, now this JE junction is now forward bias. Due to forward bias, it can act as a on switch. Due to this forward bias, it can act as a on switch. Now that this circuit is, it is between base and emitter, it is an on switch. Then it will be like this. RC short circuit, V. Is it clear? Now from here you can see the loop equations. If you write this loop equation, this in the current is IV. If you write this loop equation, that is V in is equal to the current through the base terminal, that is IB into RB plus here base to emitter, this voltage we will write as in VBE. This we will write as IB RB is equal to V in minus VBE. Now IB we can write as V in minus VBE by RB. Now you can see from this, the VBE is constant. VBE is either 0.6 or 0.2 depending upon the material. Bottom is for germanium and this is for silicon. Now this value is fixed. Now if we change V in, now suppose IB, you can see IB. Now it means as V in increases, definitely IB increases, because initial IB you take 5. 5 minus 0.7 by 1 kilo ohm. Suppose you can take, if V in is a 5 volts, 5 volts minus, if it is a 0.7 or 0.6 by RB 1 kilo ohm, then you will get a 4.3 milliampere. That is the IB current. Similarly, if V in is 10 volts, 10 minus 0.7, then you will get 9.3 milliamperes. Now what you can say, as V in increases, okay, as V in increases, IB increases, okay, that we will see here, as V in increases, IB increases. As V in increases, IB increases. As IB increases, IC is equal to beta IB. IC also increases. Got the point. Now we will see here what happens to the output current. Output current. Now this output current we can write the expression. This is here VCC is equal to VCC, here from the VCC is equal, this is RC. VCC is equal to IC RC plus the voltage here to here. Okay, this we will write as VCC is equal to IC RC plus VCE, and the input side we will write equation as, already we have taken that, V in is equal to IB RB plus VBE. This is the equation. Now output current we can represent as, output current that we will represent as VCC is equal to IC RC plus VCE. Now from this output voltage, if you want to write output voltage is VCE. VCE is equal to VCC minus IC RC. Now you can see from this above expressions, as V in increases, IB increases, IB increases, IC increases. As this IC increases, then definitely VCE is equal to VCC minus IC. This IC increases. Now this IC increases, subtraction is increases, then this value decreases, that is VCE decreases. VCE decreases, that is output voltage decreases. As V in increases, VCE decreases. Got the point? It means you can see this is RC, this is a short circuit, and the output voltage. You can take output voltage here to here, this is VCE. Okay. Now when it acts as a short circuit, the short circuit voltage is 0, but we will see this VCE as VCE sat, VCE saturation. It will be 0.2 volts for silicon, 0.1 volt for germanium, and it cannot decrease beyond this. It cannot decreases beyond this when in saturation, when it acts as a short circuit. Okay, this is the switching operation of the transistor. Similarly, a basic simple we will discuss here. This is a RB, this is a transistor, this is, and if you connected here, suppose a better example, an LED constructed, it it is VCC, it is P in you are applying as an input. Here the loop current is IB, okay, it is RC. Now when V in less than 0 or V in less than VBE, at these two cases transistor is open circuit means off switch. When it is off switch, the first second LED will be glows, that is, it is an inverter operation. It is a inverter operation. Okay, next. It is an inverter operation. Similarly, when V in greater than VBE, that is transistor mode is short circuit, that is on switch. Here LED will be off. It means here 0 it will be 1 and here 1 it will be 0. That is why transistor as a switch is nothing but it is an inverter operation. Okay students, I hope you understood. The next, how the amplifier action we will see here. Amplifier action. If V in is increased, further, then what happens? VCE remains constant. That is, then maximum IC current, at saturation, that we will discuss as IC sat is equal to VCE minus VCE sat by RC. Because you can see the equations, you can clearly see. There is a maximum IC saturation current is equal to VCE minus VCE sat by RC. That is, IC sat is maximum collector current. Maximum collector current. Okay, as we know that V in increases, definitely IB increases. As IB increases, definitely IC increases. Okay, now what you can say from this equation, IC is equal to beta IB. As beta is going on increasing, then it is not equal to this IC. Now this condition is not satisfied. This condition is, now we will write as beta is equal to IC by IB. It is a normal form. Where here in this case IC less than beta IB. As beta increases further, as IB base current will increases, then IC becomes less than that of beta into IB. Then we will call it is a forced represent. When IC less than beta IB, then this beta is known as beta forced. Beta force is equal to IC saturation maximum current by IB. Now you can see here, as IB increases, beta force decreases, because both are inversely proportional. Both are inversely proportional. Now this can be clearly explained by using overdrive. What is overdrive? Overdrive is nothing but it is a ratio of beta by beta force. Beta by beta force. We know that beta is equal to IC by IB. It is normal, C configuration based. Beta force is equal to maximum IC saturation current by IB current. Okay. Now this value, this overdrive greater than 1, greater than 1, equal to 1. When it is equal to 1, when overdrive equal to 1, we will call it is bottom or edge of the saturation region. Edge of the saturation region. Edge of the saturation region. When it is greater than 1, transistor is in a saturation region. It is suppose now when greater than 1, at this case transistor is in a deeper saturation region. Okay, depending upon the overdrive, this value, this ratio beta by beta force we will call as a overdrive. When this value is equal to 1, now it is just entering to the saturation region. It just entering to the saturation region. Now when it is greater than 1, it is within the saturation region. When overdrive greater than 1, then the transistor is deeper into the saturation region. Okay, students. Now you can see this region graphs. If you draw a plot between IC versus V in input voltage, the graph may be like this. Okay, this is a region 1, it is a region 2, it is a region 3. Okay. Region 1 is a cutoff region. In cutoff region, IC is equal to 0 and IB is equal to 0. No current. Then the transistor will act as an off switch. Now you can see in this region no current. IC is 0. The second region 2, this we will call as a saturation region. Here what you can see in this region, in this saturation region, IC current is equal to IC sat. Collector current reaches, because it is increasing, rising, you can see clearly. It is a maximum saturated current. this current of IC we will call as an IC sat. Now IC is equal to IC sat, and V0 is equal to VCE is equal to VCE sat in the saturation region. Okay. Now this region we will call as R on is equal to VCE sat by IC sat, and the value of this is it is a perfect on switch. The resistance means it will be like few ohms, not high resistance. It's in saturation, transistor can act as an on switch. When it is an on switch, the resistance of the transistor is very few. Okay, it is a perfect on switch. Now short circuit, the resistance for short circuit is very less. Okay, that is because you can see here R on. Now here R on is equal to VC sat is, for example, you can take 0.2, and IC is maximum. IC sat is maximum, like it will be like a 10 milliampere. Then you can do it. You can get very less resistance. You will get it. Okay. And the region 3 is an active region. Region 3 is a active region. In this region you can see IC is equal to IC sat. You can clearly study from here. IC is equal to IC sat. And from the graph you can clearly see V in. This is a V in. It means the current IC increases with the V in. The current IC increases within the V in. That you will see here. That is region 3. Region 3 is an active region. Region 3 is a active region. In this region you can clearly see, because IC and V0 are actively respond to change in input signal. It means output voltage V0 is equal to VCE. Vin is an input signal. IC is the output current. It means as Vin increases, there is a change in VCE and there is a change in IC. Now as IC is increasing maximum, V0 is decreasing. Now what happens? Due to increasing in Vin, definitely there is a change in VC and IC. Similarly, we will call that a transconductance. That is GM is equal to output current by input voltage. And GM is nothing but it is a ratio of output current to the input voltage. This is known as transconductance. In this region, transistor can act as amplifier. This is a transistor amplifier region. Okay. Next, for a better transistor amplification action, the transistor is operated in an active region. Okay. It means a smaller input change, a larger IC current. For a smaller input change, a larger IC current can be produced. That is an amplifier action. Okay, students, I hope you understood. This is the way how the transistor can act as a switch, and this is the way how the transistor can act as an amplifier. Okay students, thank you. Easy BTech, guide for BTech and beyond.